Wolfgang Ketterle described watching how a condensate formed for him, like how nature is giving birth to something very fragile, but we were able to observe it in its natural environment. The principles of laser cooling are pretty simple. You shine laser light on atoms, the atoms scatter light, and if you play some tricks, the light which is scattered or emitted has a shorter wavelength and is more energetic than the absorbed light. The scattering of light removes energy from the system, and the system cools down. There are two types of magnetic traps. Some have a pointy potential and a linear V-shaped potential. Others have a round potential at the bottom. Those traps are more tightly confined. Interference between two condensates allows you to photograph matter waves directly. The interference is clear evidence of the wave nature, where you build two condensates, so you basically have lots of atoms in the ground states in each of the two traps, and then you turn off the traps, let them go. Then you can measure the distribution of atoms as a function of position. You see fringes in the atomic density because the two condensates were interfering with one another. What determines the spacing between the fringes? There is a de Broglie wavelength for the atoms, and there is a de Broglie wavelength difference between the two condensates. This is quantum interference between atoms. The optical trap could be used as a transport mechanism for Bose-Einstein condensates again, thanks to Wolfgang Ketterle and his colleagues.